Continuing our study of forces and laws of motion, now we will move into section 12C, the types of forces. And we're going to have a little bit more math coming your way, a little repetition of some things we've already said, but some new information up here as well. So let's begin. Notes 12C, types of forces. Ready? We know about gravity. We know that gravity is a pull from the earth on every object to cause objects to fall down. In fact, the definition of down is simply toward the center of the earth. The earth attracts all bodies, and the earth is very, very massive, and that mass gives the earth's gravity and a very good amount of strength. But did you know that all objects attract each other? Every object has gravitational pull on every other object. Even the smallest pieces of matter still have gravitational pull on each other. And when you see the formula in a little while, it'll make a little more sense that because the earth has so much mass, the earth is going to win that tug of war every single time. Now, gravity is a field force. Remember what field force means. Field forces mean the objects do not have to touch each other in order for the force to take effect. The objects have to be close enough together. And since the Earth's gravitational pull reaches far, far off the surface of the Earth, well, that's why things fall down. Now, we already saw this number previously. All objects will fall to the Earth due to gravity by an acceleration rate, excuse me, of 9.81 meters per second squared. Remember, that means an object will gain 9.81 meters per second of speed for every second that the object falls. And this is disregarding air resistance. Remember, objects that meet up with a lot of air resistance will realistically fall at slower rates. But the Earth pulls on every object with the exact same force. An acceleration due to gravity, disregarding or having minimal air resistance, 9.81 meters per second squared. Ready? Newton's universal law of gravitation. Now this, I will tell you, when you see the equation on the next page, that's going to look pretty weird at first. But once you realize exactly what's going on, it's not as bad as you first think it is. And remember, you have to know how to enter scientific notation on your calculator. Here is the universal law of gravitation in word form. Gravitational force is directly related to the object's masses. Larger masses have larger gravitational pull on the other objects. And that'll make sense when you see and understand the formula. But gravitational force is directly related to the object's masses. Mathematically, that means we will multiply the two masses. Inversely related to the distance between the masses. That's a little common sense right there. If objects are further apart, the force is going to be weaker. And actually, not just the distance, but the square of the distance, as you're about to see on the next page. So let me say this straight through one more time without interruption this time. Gravitational force is directly related to the object's masses and inversely related to the distance between the masses. Well, if directly related means multiply, what do you think inversely related means? That will mean to divide. Now, there's also a scientific number that'll be a constant that we're about to add to this formula. Ready? And there it is. In mathematical terms, the universal law of gravitation, I'll explain all the letters in a moment, F equals G m1 m2 divided by d squared. Okay, what this means is the total force between any two objects is equal to the gravitational constant 6.67 times 10 to the negative 11th, the unit is Newton meter squared per kilogram squared, times the mass of the first object, times the mass of the second object, divided by the distance between the objects squared. And again, at first, this may look a little intimidating, but as you'll see when we do the practice problems, all we're going to do is multiply three numbers, and the first number is always this right here. And then we'll divide by a fourth number. Let's see, very, very quickly. Let's say we have two masses. I'm going to make sure this shows up on the screen. Okay. Big G, we'll say one mass is 25 kilograms, and the other mass is 50 kilograms. And the masses are placed 10 meters apart. All I'm going to do is now put this number here, 6.67 times 10 to the negative 11th, times 25 times 50, and then divide by, we know that 10 squared is 100. This will take some practice and some getting used to, but notice again, we're just multiplying three numbers, then dividing by a fourth number. And if we have a good scientific calculator and we enter everything correctly, we don't have to hit enter or equals until the very end, and then we will get our answer. Now, let's do this. We have Newton meters squared per kilogram squared. That's the unit for the gravitational constant. Then we're going to multiply by mass, which is kilograms, then another mass, second mass, 1 and 2, which is kilograms, and divide by a distance, which is meters. That ends up getting squared. Now, look what happens here. Kilograms squared, let me get the better color, kilograms squared cancels with kilograms twice there. Meters squared cancels with meters squared there, and look what's left, newtons. What is the unit of force? It is the newton. So when we do all the unit analysis, we end up with newtons. So this unit looks really strange, but if we work the problem correctly, the units will take care of themselves, and we end up with newtons, which is the unit of force. Practice problems are coming, as you see. Many examples are coming. You do want to memorize that number, and you will, because we'll do enough problems. Ready? What is weight? You step on the scale to get your weight. What really are you measuring? Now, in the English system, we use pounds, but in the metric system, we use newtons. Weight is a force. Here's your definition of weight. The gravitational pull on an object, the Earth's gravitational pull on an object. Remember that force equals mass times acceleration. Now you see the title up there, weight is a force, and gravity has its own specific rate of acceleration. So if I remember that, then I will see right here, weight is a force. Gravity is a rate of acceleration. The mass of the object will remain the same. So all we're doing is changing the F to a W and the A to a G, and we'll simply multiply to get the weight. And remember that gravity's number is always 9.81 meters per second squared in the Earth's atmosphere. Okay? Now, other planets have different rates of gravity because those planets have different masses. But the Earth's gravitational pull is always 9.81 meters per second squared. As long as we're talking about on the Earth, we'll never have to figure out G. We may have to figure out M, and you're going to see an example of that in just a minute. But weight equals mass times gravity, and that comes from force equals mass times acceleration, Newton's second law of motion. Ready? Now, you see a picture of a calculator, you know what's coming. We're going to do a math problem. I have an object with a mass of 50 kilograms. I want to find the weight. Well, here's what I'm going to do. I'm going to label. Now, when we have word problems, we're going to label everything. Here's mass. We're looking for weight. We know gravity is always going to be this number right here. When we do word problems, I want you to label, put the letters above the numbers. Now, we will see which equation we need to use because you're going to have to pick the correct equation. I see an M, a W, and a G, so I know I'm going to use the formula that has an M, a W, and a G. Weight equals mass times gravity. W equals mg. Now I just put the numbers in place. We don't know W, that's what we're figuring out. We know M, 50 kilograms, and we know G, 9.81 meters per second squared. What do we do with this? We just multiply. Before we multiply, though, we're going to estimate. 50 times, round this number off, we get 10. The reason to estimate, we see what to do, and then we'll know if we did the regular problem correctly. 50 times 10 is 500. So I know that my answer needs to be very close to 500. Since I'm really multiplying by a little less than 10, then I know my answer has to be a little bit less than 500. And turns out that will be correct. Multiply 50 times 9.81, we get 490.5. Now, weight is a force, so the unit for weight, just like the unit for force, is the Newton. And that comes from, maybe you remember from the last set of notes, a Newton is a kilogram times a meter per second squared. We're multiplying mass, kilograms, times acceleration, gravity, meters per second squared. We get a kilogram meter per second squared, which we call a Newton. So this works out. The unit analysis, the units will take care of themselves. But again, estimate first. 50 times 10 is 500. I'm really multiplying by a little less than 10, so I need to have an answer a little less than 500. Ready? What if I already know the weight and have to calculate the object's mass? I have an object that I know the weight is 200 newtons. How much mass does this object contain? Now I'm simply going to do an inverse operation because I already know the weight. Once again, I already know the weight. I'm calculating the mass, and gravity is automatic. Once again, I know I need to use a W, an M, and a G. Here's the equation. You'll have a list of formulas to choose from, but you will have to pick the correct formula. This time I already know the weight. Since I know the answer, what's missing is part of the question. That means I have to work backwards. Well, what is backwards or opposite, or in mathematical terms, the inverse operation of multiply? That is divide. So if I already know the equals number, like on the last page, I'm going to do what I'm told to do. But since I'm missing one of the factors, I have to divide the inverse to get that. Let's estimate first, though. We're not going to divide 9.81 just yet. Remember, the inverse will be division, and then round that off to 10. We're actually going to get m equals 200 divided by 10, which is 10. That's my estimate. So I know my answer has to be very close. Actually, I said that wrong. 20. Hey, make the mistake. See it, fix it. So I know I have to get an answer very close to 20. But realize this time we're dividing by a number that is less than 10. That means we're actually going to end up, because we're dividing by less than 10, a tiny bit more than 20. Understand how numbers work. You'll know if you did the question correctly. Now let's do the real question. Let's divide by 9.81, which is the inverse operation because we already know the weight. And this comes out to be 20.39 kilograms, which is just a little bit above 20, like our estimate said. 200 divided by 10 is 20. 200 divided by a tiny bit less than 10 is a tiny bit more than 20. That's going to happen when we do division. Ready? You've seen this equation already. Falling distance, d equals 1/2 gt squared. But I'm reminding you of that again because we're going to continue using this. Falling distance, how high did the object fall from? And we will use this equation to calculate. And if we know the distance, we can calculate the time needed for that object to fall simply by doing a couple of algebraic steps. And we will do those in the practice problems. This is the same example you saw in the last set of notes. The stone falls from a cliff, hits the ground 5 seconds later. How high is the cliff? But having this on the screen now will help me show you exactly how to set up the problem. A stone falls means that's gravity. Falling, gravity. The stone hits the ground 5 seconds later. What is 5 seconds? That is a time. So put the t right there above 5 seconds. How high? That is a falling distance. So put a D up above how high, and do this on every word problem, and try that in your math classes too. You'll have a much better time setting up the equation. Now we see which equation we need. I need the one that has a G, a T, and a D. D equals 1/2 GT squared. I also now know where to put those numbers. Do I know D? No. Do I know G? Always 9.81 meters per second squared. Do I know T? I do, 5 seconds. And the exponents for seconds, now realize it's T squared. That means T is in the parentheses, so that 5 still gets squared to 25 like you see right there. Estimate first. 10 times 25 is 250. Half of 250 is 125, so we need an answer very close to 125. Multiplying by a tiny bit less than 10, we need a tiny bit less than 125, which we have right there. We will do more practice problems. Ready? All right, friction. Now, our equations assume that there's no resistance, but we already know there's always some resistance. Higher levels of physics, you'll end up using what's called coefficient of friction to get a much more accurate answer to the problem. Friction always opposes motion, no matter what. An object is moving, there's always a force pushing back on that moving object, trying to bring that object to a stop. And friction is the name of the force that opposes motion. Now, since forces and motion are vectors, they have directions. Friction is in the opposite direction. Friction's also a vector, but friction is a contact force. The force of friction is actually touching whatever object happens to be moving and pushing back on that object. And since friction includes direction, that is opposite of motion, remember direction means we have a vector. All forces are vectors, including friction. The direction of friction is the exact opposite of the object's motion every time. Sometimes there's friction that we like to have. Think of brakes on the car. We want that friction so we can slow down the car. We also want good tires on the car with a lot of deep treading, because that treading will grab the road and maintain safety and control. Bald tires, tires that have lost their treading, those tires are slick, they're going to skid on the road, and eventually you won't be able to control that vehicle very well. Well, friction that's beneficial to maintaining safety and control, we call that traction. Now, traction is a kind of friction, but the name traction tells us that this friction is wanted. We want to be able to control that car and slow down and stop that car much more safely. For example, like we've been talking about, the friction of the tires on the road. Another great example I mentioned a moment ago, the brakes, to apply friction to help slow down the car by pushing back on the car or making it difficult for the tires to turn. Okay. Bike brakes, especially hand brakes. You squeeze those hand brakes and pieces of rubber come together and rub against the tire to slow down the motion of the tire. But friction always opposes motion. Sometimes we like the friction. We call that traction. Ready? All right, almost done. 3 types of friction, and their names actually define themselves. Sometimes in science, words have fancy wording, but a very simple meaning. Well, in this case, the wording and the meaning are very simple. Static friction is a force holding objects stationary. Remember, static means not moving. So if I have a ramp, go ahead and draw that. I have a ramp, and I place a box on that ramp, especially if the ramp is kind of rough, not really smooth. Well, the gravity's trying to pull that box down the ramp, but friction is acting in the opposite direction to push back up. That box will stay still. We say there is static friction. These 2 words are even easier to understand. Sliding friction, when an object slides, okay, such as you try to slide that box across the floor, well, the floor is going to push back on the box and make it a little more difficult. If the floor is very slick and so is the box, it'll be a lot easier. Things like carpet, though, provide more surface area, grabbing the bottom of the object and applying more friction, making it harder to pull that box across the floor. That's why we use wheels. But wheels put rolling friction, just not as much. One object rolls. Think of a ball rolling across the floor. Why do we have wheels on heavy objects? Why do we use something like a dolly with wheels to move a heavy object, a big box like a washing machine or so? There are fewer points of contact on the wheel to the floor than there are the bottom of a large box and heavy box and then the floor. Rolling friction is a lot less than sliding friction, so we can move the same heavy weight a lot more easily by putting that weight on wheels and experiencing rolling friction instead of sliding friction. That's common sense, but now you see the definitions, like I said before, when the math verifies the common sense. 3 types of friction: static, sliding, and rolling. Ready? Centripetal force we started to mention earlier. This is happening whenever objects are moving in a circular pattern. Let me try that again, a circular pattern. The faster the object moves, though, the stronger the force will be. The acceleration of the object toward the center of the circle. If we're going slowly, if we're going in a circular pattern kind of slowly, we'll be pulled toward the center, but we won't feel as strong of a pull. Now, if I go very fast in comparison, then that pull is going to be even harder and stronger. We would stop more to the center, but I drew that longer just to show you the difference between the two. The acceleration, the force is going to pull us toward the center. The faster we're going, the stronger that force is going to feel. Centripetal force is acceleration toward and force being pulled toward the center of the circle. For example, you know this already. The sun's gravity keeps the planets in orbit. Without the sun pulling, instead of a circular pattern, the planet would go off in a straight line. But because the sun's mass is so much larger than the Earth's, that sun's going to keep the Earth in orbit by gravitational pull. And I've mentioned this before. Swing a ball on a rope in a circle above your head, then let the rope go. As long as the rope is attached, we're going to continue to get that circular motion, assuming that I draw well. And here's the center of that circle. But as soon as we let go, that ball's going to go off in a straight line until gravity, of course, makes the ball hit the ground. Okay? Swing that ball on the rope, let the rope go. The centripetal force will be pulling objects toward the center of the circle. Ready? Fundamental forces. Okay, these are forces that outrule all other forces. These forces cannot be helped, cannot be stopped. They are going to happen. There's a strong nuclear force that holds protons and neutrons together in the nucleus. Something has to keep those protons from repelling each other with their like charges. The strong nuclear force does that. A weak nuclear force holds parts of the protons together, but doesn't really have any effect on the neutrons. So we have strong nuclear force that keeps protons and neutrons together, weak nuclear that just keeps the protons from separating among themselves. Keep one proton together instead of splitting apart. And then there's electromagnetic forces, which we'll talk about later on in the year. These are electrically charged particles that attract or repel each other. And we've mentioned that with protons and electrons before, but we'll do electromagnetic forces when we study electricity and magnetism later on as well. But these are some fundamental forces that can't be helped and can't be stopped. Electromagnetic could be stopped with some moisture. Otherwise, that is going to happen whenever like and unlike charges get together. Fundamental forces: strong nuclear, weak nuclear, and electromagnetic. Ready? And we're done. And there's my joke. Gravitate toward an A. Ha ha ha, yuck, yuck, yuck. All right. Take care. Catch you next time.